Hey, Mohammed, can you hear me?
Hi, yes, I can hear you.
It's Jeff. How are you?
Jeff, it's you, right?
Yes, yes.
Your name doesn't show up as okay.
Yeah, I come up cryptic there, don't I?
Uh, I'm not sure if there is a meeting today. There was some cancellation also I received, um,
Huh.
but it still shows up in my calendar. So,
Hey guys.
oh, hi,
Hey,
Tony.
Tony.
Oh, I don't see David. I'm wondering if I sent you the right invite. Hang on a second. The CDX meetings or invites are bizarre. Hmm. Let me check with David.
Sure.
How's it going, Mohammed?
Yeah, pretty good. Very busy with so many things in parallel. So, but still, um, yeah, every Friday I reserve some time to go through some, that lot of onboarding, e-learning stuff, right? So
Oh, so much stuff, so much
yeah,
stuff. I could not believe how much. And I thought
yeah,
it was done a couple times, and I got, announcements to that I forgot stuff. And you think it's one course, and it ends up being, a whole day's worth of courses.
right, yeah,
Well, that's good.
yeah. Did you hear about any I3D upcoming training you were mentioning earlier?
Um, no, I did not. I I should ping Pear again on that because he said it was supposed to be out in September, October, following the release. But
Yeah,
he came back to me the one time and said, no, not yet. But
okay,
I didn't get any like Outlook date on it. So I will kind of remind him because I'm curious myself.
right. Please keep me posted on that if you find something
Yeah,
I
I
join.
will. I will.
Yeah.
I'll put
Also
some.
to Andros, I think we should all try to join. Yeah,
Yeah, well, absolutely. I'll put some kind of a link once I get it
sure,
in our Teams page.
sure. Yeah. Yeah, I think Tony, probably today's meeting is cancelled because I did receive.
Yeah, it is canceled. I just called David. Yeah, they had the OCP conference this week. I was there 2 years ago. There was about 2,000 people there.
Wow.
Last year it was about 4,000, and David was there this year. He said it was 7,000.
Wow, okay.
Um, anyhow, I'll just talk to you briefly about what we're trying to do here. So uh, let me pull up, see if I got a picture of what we're doing. Let's see. Jeff, I don't think you've been on any of the calls, have you?
No, I have not. This is all new to me.
Okay. I'm going to show you this one. And hang on a second. Okay, I got one. Give me one more second.
Sure.
All right, just a couple of things. Let me share my screen. All right, I'll start with this one here. This is what we did a couple of years ago at the OCP summit. And let me zoom in a little bit. So we did a demonstration that we had on the floor. So what we did is, this is the design that we're creating. It's got 4 chiplets and 4 HBM memories. And what the chiplets are is we have 16 instantiations of a RISC-V processor, and it's not a real design. We just got like we have an open source net list for that controller, so that design is real, but essentially we're just plopping down those instances, and then hooking up some basic signals that we can access it. We don't really have an HBM memory integrated in there, so we're just creating a simple memory design. So we have something that we can store memory. So it's a contrived example, but the idea is we're demonstrating these 4 chiplets. Each of these chiplets has one HBM interface, and then there's UCIe Express interfaces on 2 sides. So these chiplets can connect to each other, and then we have memory interfaces on each of the sides. So this is a representative example using some open source IP. And what we're really trying to demonstrate, this is a couple of years ago, is kind of predictive analysis. So we did a couple of things. We did some thermal analysis. So we just created a simple power model for each of these chiplets, and then ran caliber thermal. So this is what it looks like in caliber thermal. Trace Systems has a tool, so they actually use their 3D modeling tool. This is their actual floor plan that they created, and then we we exported that. David exported that into XSI, and then we ran caliber thermal. The other thing we did is on these routing channels, we did what I call predictive channel analysis on the BOWs. It was a BOW. We've changed this to a UCIe Express. And by predictive analysis, this is actually using the HEEDS optimization. So and Mohammed, I think we've talked about this with you, if I'm not mistaken, right? John Chaka, they call it Design Explorer or
Design Explorer. Yes.
Yeah. So what that and Kendall has done some things with it. So what HEEDS is Jeff, just for your benefit, HEEDS is an optimization platform that Siemens, it's actually in the PL's side of the fence, has. And they have a whole group that supports that. And what they do is they integrate different engines. It could be a simulator, it could be any EDA tool. So they kind of integrate these analysis tools, and they have a dozen or so tools that have been integrated, both Siemens and non-Siemens. So they do actually have HFFS and some other interesting tools. The hyperlinks has also been solvers, field solvers have been integrated into that. So the idea is you have this optimization engine, and you integrate different tools for analysis. And then what you do is you define your design criteria. So what are you trying to optimize for? In this case, we're trying to optimize for speed of the channel and signal integrity analysis. So they set up kind of the eye diagram and specifications. And then the other thing is you need some kind of design input. And generally you want to have parameterized design parameters. And the idea is you will this tool will modulate the variables, and you could specify the range and the increments of what you want to modify. And then looking at the desired outcome, the results, it'll run the simulations, and it has a very efficient algorithm to really converge on an optimal solution with a minimum number of simulations. So it's very efficient. It uses something called the Sherpa algorithm to try to converge on an optimal solution. And it's just general technology. And the application that was used here is we integrated the hyperlinks field solvers, and then there was 3 or 4 different routing templates. So different essential, and by a template, these are different routing strategies. So you may have interleaved power and ground shielding. You may have shielding on the top. So there's different topologies, and 2 layers, 3 layers, whatever. So they have, I think, about 5 or so, maybe more, different kind of templates, and those are parameterized, and you can vary the width, the spacing, and things like that. And then by setting up the criteria, it will very quickly go through and look at each of those templates, modify all the parameters, and come up with an optimal solution based on what you specified. And your optimization criteria can be anything. Could be cost. So if you had a cost function in there, you could say, well, if we can do this, say, in organic process with as few layers as possible, and still meet the minimum performance requirements. So that's what we did for this demo. And one of the things I want to do at the offsite is we want to have a brainstorming session where we think about how we can do these different, leverage different problems leveraging the HEEDS technology. So I'm just kind of giving you a heads up to start thinking about other applications. But anyhow, back to the mundane. Let's see what else I have here. So we are using just show you a NAN 40 library. Have you ever heard of that, Jeff? It's an open source library. We have standard cells, and they also have open RAM. So all we have are standard cell libraries. It's a 40 nanometer process, and we have memory compilers. So we're using that initially just for the net list. We're using the standard cells and the memories, and we have a couple of well, it was two. One guy graduated, but we had 2 PhD students from Georgia Tech that are working on this project, and David is kind of doing a lot of the floor planning and power analysis. So we've developed some simple RTL, and they actually synthesize it with an open source tool. So we have a gate level net list of this design, and and it's got some memories. There's no IO libraries. So the idea is we're going to try to continue building on this. The first thing we looked at was doing, very what I call predictive or black box thermal analysis, right? You just come up with a rough power estimate for the whole chip. And then, you create different, you put in your interposer, and you can do some simple thermal analysis. So we want to continue growing on this. Now we're 2 years into this. So with the gate level net list, we can actually start running in power and coming up with much more accurate power models, but we will need a layout as well. So that's something that I offer Jeff, you in your spare time. This would be a good opportunity to start having a test case where you can kind of wet your feet a little bit. It's not a real design. We're going to have to hack together some constraints, but primarily we're just looking at just taking a net list and creating a layout, and then we can take it and empower. Since these are little processors, rather than setting up a whole design where we have IO bringing in and controlling all this stuff, we can just execute code directly on those processors. So that's the way we're going to generate activity for all these chiplets. And right now it's an array of 16 chiplets, and then we have 4 chiplets. But it is a scalable design. In theory, we could create a bigger chiplet that has 8 or 64 of these things. So it's a very simple, scalable design if we want to do some more interesting things. So by having, we have 0 power, so we could do some very simple, power analysis, but it's not going to be terribly interesting. Really can't do IR drop until we have a layout. So once we have a layout for the chiplets as well as the interposer, and so the interposer that we're using or technology that we're using for that is a glass interposer technology that was developed at Georgia Tech. So that's also open source. So we do have design rules. So the gentleman from Georgia Tech is going to be doing the layout of that interposer using XSI and XPD. So he's going to be doing kind of the top level packaging. Right now, we just have simple, black box definitions of the chiplet, but we want to replace that with an actual left F or GDS, and then once we create the power models, we can start doing power integrity analysis, possibly some noise analysis. So the idea is we want to demonstrate our flows with this example. So we're going to try to demonstrate as much as we can. So SI, PI, and then we can continue building on this. We may want to start mucking around with VRMs. We can flush our UPF flow. So there's a lot of things that we can use for this. You know, and then the other thing, important thing that we want to demonstrate, since this is an OCP demo, is our 80Ks, right? So in this, if I go back to this first demo, where is it? The other thing that David did is, and it's not in this slide, but let me see, I think I have it over here. Yeah. That's not it. Anyhow, so what David did is he hacked up a JEP 30 CDX part model for the part, and he created like a little kind of dummy catalog. So the idea is he'd show you you'd pick one of these chiplets, and he had an XML view of the footprint of that device, and that's what he imported into his tool. So we could do that as well. So we're kind of demonstrating the JEP 30 part model as for one of it. The other thing we want to do, and what we've been working on for the last couple of months, actually, it's moving slow, but is rather than just, coming up with, hacking in the material properties and the design rules, we're trying to capture the material properties and the design rules in our 80K and MDK files. So we do have an actual set of design rules for the interposer and material properties for that interposer. And so that's the other thing we want to do, is have kind of a demonstration, a proof of concept demonstration of how these material properties are used in the design. So and all of this is going to be kind of just getting warmed up for the DARPA activities. So we're very close to submitting the MDK, a little bit further behind on the 80Ks, but the MDK is in pretty good shape. We're ready to start submitting that to JEDEC. But we did want to go through and just kind of pipe clean the flow with this demo just before, just get some reasonable feedback that we've kind of thought it through enough before we start actually pushing it through the standard process, which is long and laborious. So Michael Durkin is the guy who's runs that JEP 30 group in JEDEC. And so he's the guy who's gets into the gory details about all the XML and the schema and stuff. But sometimes he drags the discussion down a little bit too much on that side. He's more of a PCB designer background, so he doesn't really have a good IC or package background. But he is a Siemens employee, so he's helping us get these standards put in as JEDEC standards. And we are to some extent competing with SI2, who's in 3D blocks. But one of the things that we are doing that is really not competing at all with 3D blocks, at least today, is the material design properties. That is something unique that we're driving. And, we are proposing to work with UC Davis, Professor Kang, Andrew Kang, and another professor. There's a small team that is developing open source tools, and they are actually going to be part of the DARPA type project. So we will be working with them in kind of adopting the standards, and they're going to create an open source tool for creating the material properties, and as well as the assembly design rule models. And the idea is to have an EDA neutral authoring tool. So that's going to be partially funded through the DARPA contract to do that. So we'll be working closely with him. He's also, we've also talked about having some abilities to do bidirectional translation between applicable things that are supported in 3D blocks. So that's another area. So right now, most of the XSI team is working, and a good chunk of the team is spending a lot of time supporting the 3D block standards. So we're not getting much bandwidth out of them. We're not getting any bandwidth out of them. But you know, if we could actually leverage the 3D blocks formats to create some of these types of designs, and then we can import those in XSI and then maybe export an XML schema. So that's one thing that I'm thinking about. You know, we'll have to wait till Sundram gets started. And good news is, I think his H1 visa stuff has been improved enough, and he's going to officially start on Monday, so we can introduce him at the staff meeting. He's probably going to be on my way to the airport, but I'll ask Pratush to invite him. And Bala is our DFT guy. He's close behind, but he hasn't gotten the green light yet. But he should be hopefully coming on in the next week or two. I'm hoping by November 1st. And I think I informed you guys. I know I told Pratush we did get approval to do the offsite in the second week of December. So we'll start locking that down, and we should we'll have all the team, with the possible exception of the package designer, though. I'm hoping that we can close and hire our package lead before the offsite. Andres is doing another offsite the same week, with a lot of the guys coming over from Europe from the STS, which is the multi-physics simulation division that does Flowtherm, Flow EFD, SimCenter 3D, all those reliability analysis tools. So they're going to have a separate workshop with about 6 or 7 people, and then we're going to kind of all meet together for one day, and then we'll continue and branching off and continue working on the other stuff. So still working on an agenda, but you know, one of the things, like I said, I'd like you to start thinking about how we can leverage heat. So we're going to have kind of a little brainstorming session on that. All right. So Jeff, one last thing. There is another open source library offered by Global Foundries, and I'm trying to get some information. The advantage of that is it's real. It could be manufactured. It is open source, and it does have you know, PDKs and rule decks and, you know, design enablement files. It has IOs, memories, and standard cells. So if we can get access to that, I think we'll probably switch. So I want to make that decision before we start any place and route activity on that. So I am looking into that, and we'll make that call as soon as we find out, you know, if we can get the stuff. As long as it's a reasonably competitive technology. I mean, 40 nanometers is kind of you know, old at this point, but I don't want to go backwards. If we get an open source that's like, you know, 65 or yeah, you know, 110 nanometers, we'll probably just stick with the NAND 40. So I'm not sure you guys have worked with any of those other open source IP libraries.
You know, the guys at Air Labs, the photonics guys, are using the Global Foundries. I think it's a 20 nanometer, and it's something that's streamlined for their photonics. They cut notches, you know, in the die, little V notches to put fibers.
But that's probably not open source though.
No, that's not open source. That's
Yeah.
not open source. 40's, yeah, 40's old, but it's not that old.
Yeah, so it's new enough for
Yeah.
and the idea is that, you know, training, right? So we can actually take this design and use it as a training exercise.
Yeah.
And then better yet, it was a couple of weeks ago on a CDX call, there was a woman from Fermi Labs, and I think she also works with the University of Chicago, Irvine, and she's heavily involved in a lot of government activities and stuff. And she's got some funding to develop some coursework. And you know, I suggested that they could take this design and put a curriculum around it, and we will be kind enough to offer our tools that they can use for the demo. So we may even get somebody to create the demos, because you know that's a big effort. You know, when we build all these workflows, and you guys are going through this now, right? You know, when the tool guys finish the release, there's no training, right? It's you need design cases. So this is something where, you know, we may be able to get some external free resources. You know, until I had a team, I've been scrambling, right? So I, you know, we got some OCP, we got some Georgia Tech guys working on this, but now that we have a team, you know, and that's why it's taken 3 years, right? Because we meet once a week. But now that we, you know, we have a team, we can start building off of this, and you know, put in a little more time and energy to get this stuff start pipe cleaning these workflows. So it's a simple example. So, you know, the only design that we really have that was done by Siemens is is a massive 7 nanometer FPGA chip that's used in the hardware accelerators, and that's just too big, and it's got a lot of proprietary IP that we're not even allowed to touch, you know, for all the PHYs and stuff. So I gave up looking for internal designs. Jeff, I don't know if you've made any progress there.
Yeah, it's slow getting the right people and trying to find stuff. I did find I don't think of the acronym. There's a person that's going to be sending me an Aprisa database, and she called it something. She's in Cairo.
Okay.
Just looking.
Yeah, well, once you get that, just send me a short email explaining what it is. And
ODT, Aprisa ODT. I don't even know what ODT is.
ODT, I don't know what that is.
And Gugner ODT. So I'll find out more. She's gonna set, her name is William Awad. She's gonna send me the database, etc. It is not UPF. I'm still struggling to find something with some UPF, but
yeah,
hopefully she'll send me what I need.
Well, I mean, we can even use this design, the OCP demo, if we can't come up with anything else.
Yeah, no, both even. I mean, I
right.
You know, I was thinking of this Aprisa thing for, you know, kind of at least initially taking a look at the Verilog and, you know, the whole flattening Uniquify that we talked about, to see if I have something that's a reference to send to the R&D folks. But so this David Rachkoff, he's part of the university, I'm assuming.
No. He has his own company.
Oh, okay.
Yeah,
okay.
He's the CEO. He's actually got 2 companies. He's the CEO of 3 Systems, and 3 Systems. His expertise is really in the area of power. So I would say you know, he was the one who was the key architect of the IEEE. What is it? I'll look it up. What's the power standard? I think it's 2416 or something.
So he's approachable, or he meets
Oh, yeah.
with us once
I,
every week or 2 weeks, or
he's on all the CDX call. The 2416, IEEE 2416 is the official power spec that was developed to support power and define power. And David is the guy who wrote that. He did it in SI2, and then he lost control of it. And he's for that reason, he refuses ever to work with SI2 again. That's why he went to OCP. He's a good guy. He also has another company called Anemoy, and Anemoy actually has a thermal simulator and a floor planning tool. So we are, we potentially have had some discussions about collaboration or possible acquiring some technology, or the company. We're working very closely together, and we are planning to use his tool, Power Meter is what he calls it, for on the DARPA program. So that's included in the license. Have you guys worked with any power planning tools? And when I say power planning, defining your how do they do it at Qualcomm, Mohammed, when you were setting up your PDN network, in the architect, where your VRMs are, and the mapping between, going from, say, an interposer to a chiplet, were you guys using UPF, and did you have a tool to support that, or?
Actually, I am not sure. I was mostly, within the, lower level cells optimization part of it, like, the signal integrity, interconnects, and so on.
Yeah.
But, looking from the, top level, how, power
Yeah.
mapping is done, I think that's something I'd be interested to learn. Yeah.
So at East Silicon, we use the most popular EDA tool in the world for that. It's called Excel. So it was all spreadsheet, right? So we did all our power analysis with spreadsheet. We had activity factors. It was pretty good, and that's how we did our power planning. But he has a tools that allows you to actually create a power model, and then what it does is it actually replaces, as you start building your designs and you have, say, RTL, you can replace that power model with an RTL generated power model on gate level. And what it does is it aggregates the entire power for the entire design. So you define it right up front. So you say, all right, I've got 10 different chips. Here's my board. I've got my power supply here, VRM, and then it'll generate UPF. But then what it does is so you have you just create your power model. So your architects are, they're taking estimates of how much each of the different components are going to draw. But then as you start building the design, what it does is that effectively becomes the spec, and you can graphically view your power where it is, so as you start replacing real components with real power and getting finer granularity, you can see where things are going up, things are going down. That power is going to change throughout the entire design, but it aggregates a snapshot of the entire design wherever it is. So your top project lead always has full visibility as to what the power is and where it's going. So it's a really cool tool, and I've never seen anything like it. And the only other company that I stumbled on that had a tool is Intel, and was actually developed by ST about 20 years ago. And Intel bought that technology, and they're using that internally. So it's not really available on the open market. So as far as I know, 90% of the world is using Excel, and Intel is using that proprietary tool. ST is probably still using it. So it is something that I think I'm trying to find a sponsor within Siemens to to acquire it. But so far, I haven't found the right general manager that's put it up high enough on his radar screen. The response is, yeah, that's pretty cool, but that's not my job. So that, we're focusing on this. So, but as we get more into the system level stuff, I think that could be a strategic acquisition. So I do want to get a demo of that from David. I've showed it to a couple different division GMs, and they just said, yeah, it's pretty cool, but we're busy doing other stuff, and that that's not really what I'm working on. But I think it is going to be important for 3DIC.
Tony, does that parameter suck in power models from SOCs also?
Yeah.
Or
Oh yeah, absolutely. Yeah.
Okay.
Data sheets. I mean, yeah, it's very powerful, Jeff. And since you've got a pretty power tint to your latest experiences, I think you're probably the right guy to look at that. I've talked to Joe Davis about it. He goes, yeah, well, we don't get involved in the planning. We just do the analysis once the design's done.
Yeah. No, that sounds like a good planner, a good way to, like you say, aggregate everything. And it's always a moving target too. So.
Oh, it changes daily. Yeah. So, it really is a system tool. So that would be part of 3DIC Architect. But right now, 3DIC Architect is one of my number one issues overall for 3DIC. The number two issue is extraction. So I've already told management we're not going to solve either of those problems organically. So we're going to have to do some kind of acquisition.
So this David, he's got a small team. I think you said a couple of PhDs that are kind of turning the crank.
No. So the PhDs are just some guys who
Georgia Tech
for Georgia Tech. So we're good friends with SK Kim, professor at he's really a place around guru out of Georgia Tech, and we're working with him in some R&D capacities. He actually was roommates with Inky, who is the lead architect for Apriza in college, so they're good friends. And he left and did a sabbatical with DARPA, trying to get a DARPA program set up to fund Place Around, and he was not successful in getting it approved through the government. So he's back as a professor, but he's actually working with Andrew, and we've got some other cool stuff that we'll be able to talk about hopefully soon. So we have a huge AI initiative, and we'll be collaborating with those guys. We're going to be, this is all highly confidential, but we're going to open up our APIs to a lot of our implementation tools, Apriza, the synthesis tools, Catapult, and the academia will start, using AI, and we're giving them access to our algorithms. So that is something that's actively going on, and so that's a big initiative that Juan is kind of involved in, and he's working with Elo, and Amit was the CEO of Solido. He runs our CI custom CIS division. So we've combined the Tanner and the Solido divisions. So it's all custom IC division. That's under Amit. So he's an AI guy, and they've done a lot of work with AI in the simulation space. And we have a whole AI team that's, figuring out. So I mentioned, we want to start thinking about how we can leverage HEEDS, which is not really AI, it's more of a optimization algorithm, but we want to start thinking about in our brainstorming how we can leverage AI, where we would leverage it. We've got the infrastructure that we're putting in place to do that, but we need the smart guys who understand how all this stuff works together, our team, to figure out what would be cool to apply automation. So we want to spend a little bit of time kind of brainstorming on that. A lot of other divisions are doing that. So that is something we want to start thinking about in our roadmap. I've been focused more on just getting the basic flows in place, but a little bit longer term, we want to figure out how we can leverage this automation to really deal with what they're calling the trillion transistor problem.
That's big.
Yeah, they're getting big.
You want to take a look at Cadence has a product called Cerebrus, which is like the Innovis on steroids, and you seed it in different ways, and it just spins a bunch of different scenarios and comes
Yeah,
up.
they're really using machine learning, and they've had some success with that. An argument to that was, well, Aprisa's algorithms are so much better, we don't need that. But they've gotten better, so now we do need it. So,
they've made
Aprisa
improvements.
has better timing closure, but there's still advantages of providing automation. That's more of a machine learning approach rather than pure AI. But there's a subtle difference. But so that is something we need to start thinking about. How to leverage that technology, because these designs are just going to get too big. We're not going to be able to do it the way we used to in the old days. There's not enough people on the planet. So by having the things like these machine readable formats for design rules and material properties, that's going to lend itself a little bit more toward automation. So that's why I'm spending so much time on this stuff with OCP.
Tony, what about your thoughts on the data management challenge? Just many files, many large files.
We're using IPLM for that.
IPLM, that's an internal tool, or?
Not yet, but it will be. We have a license agreement. Methodix is so Perforce is a company that has a product called IPLM. And if you look at the data management, the last slide in my presentation, I talk about that. That's the tool that does that IPLM. So we'll talk a little bit about that at the offsite too. But it actually, it has a disk management system. You can use any disk management system, but it has something called Helix, where that has, your standard revision control stuff. But this sits on top of it, and it allows you to categorize all the IP, and IP in the broad sense is everything and anything. So it's the software that you're installing, for your tools. It's the design databases. It's all the design kits. It's actually all the simulation results. So you can categorize it, and then it has, the ability to thread and link all this data and synchronize it. So that's how we're going to manage the vast amount of data that spans from system, RTL, TFT, chips, design kits, thermal stress, all those simulation, all this data. It's all going to be kind of digitally managed through this IPLM system, and so we that's one of the things that Sundarshan will have to, as part of the scripting. It's also the IPLM data management. So, and then that is metadata, so you can actually data mine that with machine learning and AI to figure out how to optimize your flows or to streamline your flows. So there's once we have all that data, we know how long it takes to stuff. So there's things once you have that in there. Plus, you get the full traceability, for the lifetime of the project. So if you get some third-party IP and there's an update, that you'll have full traceability as to what IP was used in the design and what's changed, and that's all traceable, which is important for government stuff and companies. So it is, I'd say most of the large semiconductor companies are using that software. So we're actively looking to acquire them, but right now we have a license agreement, and that is we're trying to get that into the DARPA contract. It wasn't part of our initial proposal, but we are trying to get that in there to do the data management. You know, they're going to use it for the entire data center, for their design center, but you know, we're using it for our workflows. So we'll probably put everybody through training, just so everyone knows how it works, but really be one guy that will be working and doing that. So, so, you know, I expect each of you guys to develop Tickle scripts, Python scripts for the low level flows, but eventually we'll hand them off to our software guy who will kind of tie it all together with this IPLM system. So that's why we want these detailed flow diagrams to show how all this linkages goes together. That's going to be helpful once we figure out how to do all that linkage, digital threading of the flows. All right. So Mohammed, I think you have the Sweetera.
Yes.
Yeah, so we got that coming up in a couple of minutes. This is the company, Jeff, we're looking to potentially acquire for doing extraction. So if you're interested, I can let you sit on that, but we're just getting a internal status update of the evaluation, if you're interested.
Yeah, put me on the invite for that, please.
All right. I think you lost your mic, but I'll forward you the invite in that. But okay, thanks, guys.
Very good. Thank you.
All right, bye.
Thank you.
Bye.